Find the general solution to the ODE y double prime minus 6y prime plus 25y equals 0. We proceed as usual. I'm going to hunt for solutions of the form y equals e to the rx. So, put that into my differential equation. What comes out? We get this equation here, e to the rx, r squared minus 6r plus 25 equals 0. E to the rx, always a positive number, so I can pretend it's not there. So we want to solve this here, the characteristic polynomial equals 0. Quadratic equation, and then what happens? Well, you'll note we're going to wind up taking square root of minus 64. So our usual procedure is going to hit a little hitch. If I want this to work, I have to bring in complex numbers. In this case, we're going to bring in a new symbol, I. It's going to be square root of minus 1, and that's going to be able to let us proceed. So if I allow for square root of minus 1, minus 64 becomes, so 64 times minus 1, square root. Square root of 64 is 8, and then I have square root of minus 1, which we're calling I. I'm going to divide by 2, so that'll give me a 4i right there. So this is what we're going to use for our roots. Now, we're going to go back to our original solution, and for r, we're going to put in 3 plus or minus 4i, see what happens. So let's take 3 plus 4i. So then I'm going to have y1 equals e to the 3 plus 4ix. We could split the exponent over two exponentials. So I'll write this as e to the 3x, e to the 4ix. And then if I have e, say to anything times I, we have Euler's formula, which says we can rewrite this in terms of cosine and sine. So I can rewrite e to the 4ix as cosine of 4x plus sine of 4x times I. We have another root, r equal to 3 minus 4i, so that'll give me another solution. So we'll have y2 equal to e to the 3 minus 4i times x. We break that up into two exponentials, so that'll be e to the 3x times e to the minus 4ix. E to the minus 4ix, we can apply Euler's formula, and what do we get? So I'm going to take minus 4x, put it into cosine and sine. If I put it into cosine, cosine's even, so the minus sign goes away. Sine is odd, so I can take the minus sign, bring it to the front. So we have this expansion here for y2. All right, now our problem doesn't start off with complex numbers, it starts off with real numbers, so I have to get rid of the complex numbers for the solution. So I have to get rid of I. So if you note, if I take y1 plus y2, this term here is going to drop out, and we'll have a 2 in front of this term, so I'll just divide 2 to get this piece here. So I'll have e to the 3x cosine 4x. If I take y1 minus y2, this part here is going to drop out, and I'm going to be left with 2 e to the 3x sine 4x times I. So here, we'll divide by 2i to get rid of the 2 and the I. So that's going to give me e to the 3x sine 4x. Now, our solutions are just going to be all linear combinations of these two functions here. So that's going to be our answer. Now, what's the point of this? If you note, we go to our quadratic equation, we get our answer, we have to bring in complex numbers. So let's suppose the roots are the form a plus or minus bi. The recipe is you take the real part, the a, that's going to give us a factor e to the ax. The imaginary part, which has the b, that's going to contribute factors of either cosine bx or sine of bx. So it doesn't matter what you use for your quadratic equation. There's nothing special about 3 plus minus 4i. It's just the procedure. So this is how you pin your solutions of the quadratic to the solutions of the ODE. All right, one last thing we should check to make sure that these solutions actually satisfy the original equation. So we'll just check on e to the 3x cosine 4x. Now, we're going to need to take two derivatives, so that's where all the work is. In this case, you do a derivative of this. you're going to have to apply a product rule and a chain rule for the exponent and what's inside the cosine. So when you work that out, what happens? Y double prime is just going to grow. But what will happen is if I subtract off 6 times y prime, we're going to be left with minus 25 e to the 3x cosine 4x. If you note, that's just minus 25y. So adding 25y to this is just going to give us 0. So this is definitely going to be a solution to our ODE.